Hi everyone, my name is Aditya Sinha. I'm the group leader of this project, Extreme Resilience, and we are participating in the New York Academy of Sciences Junior Challenge. So today I'll walk you through our innovative solution for enhancing coastal resilience against tsunamis and floods. Our project, Extreme Resilience, is designed to protect coastal communities from extreme water related conditions. So, first of all, I'll begin with the problem statement. So, we begin with this very pressing issue at hand. Tsunamis and floodings are a very devastating natural disasters that threaten the coastal communities worldwide. And the thing is that they cause massive destructions to infrastructures, ecosystems, governments, and in and all, it creates a lot of chaos, leading to loss of life, displacement of residents, and a substantial economic losses. And the frequency and the intensity of these disasters have increased a lot in the past few years because of climate change, which we all know about. And this problem particularly is really urgent in densely populated coastal regions where communities are are highly vulnerable to the impacts of tsunamis and floods, of overflooding. And our project completely aligns with the New York Academy of Sciences challenge, living in the extreme, by addressing the critical need for effective and sustainable protection measures that can enhance the resilience of these communities against the extreme water conditions that are out there right now. Coming to the background, so after the extensive research that we did, uh, we found that natural barriers like mangroves in Bangladesh and Philippines have effectively reduced the impact of floods and tsunamis, and this is what inspired us to develop a technical solution that mimics these natural barriers. But our motive was to using technology. What we are trying to do is we are trying to enhance the effectiveness and increase uh, the the kind of productivity, not productivity but efficiency. So yeah, now coming to the hypothesis, our hypothesis. So our hypothesis is that hydrodynamic drag devices, which is our main solution, can effectively reduce the energy and the destructive power of tsunami waves before they reach the coastal communities. So these devices that you can see on the right side, this is the 3D design of it. So these devices create resistance against the waves. So we do that through these fins. Later on in the presentation, I'll give you a very detailed explanation of the design. So it basically creates resistance against waves by slowing them down and reducing their impact. So by combining wave disruption, energy generation, and flood prevention in a single device, which you can see over here, we believe we can provide a sustainable and innovative solution to enhance coastal resilience against the extreme water conditions. Now coming to the description of our hydrodynamic drag devices, which is our main solution. So let's just dive deep into our solution. So we have designed a hydrodynamic drag device that aims to reduce the impact of tsunamis and floods by disrupting wave formation and resisting water flow. And how do we do that? So the device has a streamlined a streamlined elongated body for stability and minimal water resistance. It is positioned near the shore to ensure optimal interaction with the incoming waves. And key components include two front vents. So these are the two front vents the one that I'm talking about. And inside the main body there are two turbines which generate electricity and reduce the water speed. And there is a top vent as well, which you can see over here. So the vent is inspired by those in hypersonic flights or the jets, which creates an additional drag to slow water flow. And in the case of hypersonic flights, it's used to slow the airflow. And then we have two rear vents, which you can see over here at the back, which allows the water to uh, to to exit smoothly. So whatever the water that is entering from the front side can then go through the turbines which can which can generate electricity, and then come outside of the device to the rear vents that are there. And um, and there are six water jets which you can see over here, which can be activated during high tides, tsunamis or floods, to redirect water flow and oppose the incoming waves. And these jets can be also angled vertically, so we can change the angle of these jets, so we can just tilt them upwards. And what they can do is they can rotate up to vertically to prevent wave formation, so we can throw water towards the formation of the waves. Because when you look at the image of the how the waves form inside the water, you'll understand that if we are able to throw something that can disrupt the formation of the wave, over flooding or tsunami won't take place at all. So and these jets can yeah, so that's one thing. And the device features a shark fin like spikes, which you can see over here, that can rotate up to 90 degrees, or any certain angle that is required to resist water flow and disrupt wave formation. And what we propose is that this should be constructed with durable corrosion resistant material, so that it can withstand the long term exposure of salt water while minimizing the disruption to the marine life. So basically this is the description of our hydrodynamic design hydrodynamic device. Actually, I'm really sorry, I have a bad cold right now. So yeah, this is the 3D design that we made on Blender, and this is what we got after 3D printing it. So as you can see, the fins and uh, the water jets are not visible over here, but that was due to because we made this design here in India, and we were using Blender, but our teammate who printed it out, he was using a 3D printer that did not support uh, a dot blend file. Therefore we weren't able to get the best output. But this is how our prototype might look like in the real world. So yeah, now coming to the methods. So to test our hypothesis, we employed several methods. We gathered insights from coastal residents through surveys to understand their concerns and needs. So we created a Google form for it. We also asked them if they would approve of a device like ours. Additionally, we analyzed existing tsunami mitigation strategies as well, to compare the effectiveness of our device, and to identify improvements. And then again, we use, as I've mentioned below, before actually, that we have used Blender to create a detailed 3D model of a device, which allowed us to visualize and refine our design. Also, we produced a physical prototype, which I showed you just now, to better understand the real world appearance and functionality of a device. So we did case study research. We conducted a survey as well, and with that we did 3D modeling, and we printed it out as well. So these were the results of our of the survey that we conducted. So our testing, it revealed two key findings. First was that most of the people in coastal areas are unaware of protective measures for tsunamis and floods. Second, the primary source of information for most of the respondents was the news. That's it, which indicates a lack of diverse communication channels. So yeah, and here are some graphs through which we have tried to visualize the data that we received. So are you aware of existing tsunami protection measures in your community? So as we can see here, one being the least, all of the people most of the people I mean the people most of the people who have filled out the survey are from the coastal regions. So this shows that even though they live in a city or a country which is uh, which is a coastal city or a country, they are not that aware of existing tsunami protection measures. And then we have two more graphs. One is how concerned are you about the risk of tsunamis in coastal areas. So we had a very mixed response for this. A lot of people were a lot concerned, some were okayish. And then the next question was, how comfortable are you with the idea of underwater device to reduce the tsunami impact? So we just wanted to see how comfortable people were with our project. the thing that we are trying to make. So this showed that most of the people, because there are a lot of votes for 4 and 5, so we considered it to be a win-win for us. I mean, most of the people didn't have that big of a problem with a device like ours. So yeah. And then one more thing was, would you be willing to participate in community discussions about the solution? So one surprising thing was that 12.9% people, they said no. I don't know why they said no, but this still shows that there's a very lack of awareness, and you know we need programs, we need initiatives through which awareness can be raised. So yeah, and these were the case studies and the research that we did. So we have mentioned two case studies, uh, one of which is Japan's tsunami walls. So Japan has implemented extensive, so the thing is that we have, before we dive into that, so we have studied existing solutions such as, as I said, Japan's tsunami and Bangladesh's mangrove restoration projects. So Japan's extensive tsunami defense system, which is the Japan tsunami walls, uh, they include concrete seawalls up to 10 meters high, and they have proven to be effective in reducing wave energy and protecting coastal communities. However, they have also showed, limitations in extreme conditions because of multiple reasons, right? So, yeah, this is the one. This is one, and the other one is that Bangladesh's mangrove onshore project has demonstrated the effectiveness of natural barriers and flood and tsunami protections. The Sundarbans mangrove forest reduces storm surge impacts by 25 to 30% by absorbing the wave energy and stabilizing the coastlines. So that is in itself a really big thing, but still it is not able to stop the other 70% of the floods and the tsunamis. So yeah, this was the case study. I mean, this was our basic research through which uh, we were able to understand, and we were able to come up with the idea of hydrodynamic drag device. So this is our solution design. I have explained this before, but yeah, this is basically, we have two front vents, two rear vents, a top vent. Top vent is to reduce the speed of the water that is entering inside the main body, and there are two turbines inside the main body which will be generating electricity. That electricity can be used for normal consumption as well, but whenever there is a flood like situation or tsunami like situation, so the water jets that we have, so in order to power them, we can use the energy generated by those turbines for using the water jets to disrupt the formation of waves. So yeah, that's one thing. uh, and yeah, now coming to the solution impact. So our device, has the potential to significantly reduce the impact of tsunamis and floods on coastal communities, because by disrupting wave formation and resisting water flow, it offers a very sustainable and an innovative approach to coastal protection. Additionally, the device can generate electricity, as I've mentioned just right now. You know, it can generate electricity from wave energy, which can provide a secondary benefit to the device that we have made. And then coming to the future steps, so moving forward, we plan to expand community education initiatives to raise awareness, as I've talked about it before, about tsunami preparedness. We will continue to refining our device design through additional testing and prototyping, because at the moment we had really less resources, but even after that we tried to 3D print it, and we tried understanding how it might look like and how it might work in the real world. And one of the most important thing that we want to do is numerical or computational modeling, through which will be able to understand how our design will work in a real life situation. So there are some softwares through which we can do that, through which we can check the hydrodynamic, uh, like the way we can see that there are some softwares like XFLR5, which are used to check the aerodynamics of a plane. So an aeroplane, or an aircraft. So similarly, we can use such softwares to do numerical or computational modeling for our device as well, so that we can understand how our device would react, or how would it behave inside the ocean. And then we also aim to to explore partnership, and talk with professors, students, PhD students who have been working in this area, to gain insights from them, and to maybe get some funding as well for larger scale implementation of our solution. And this is a video of our hydrodynamic drag device that we have designed. So this is just a 360-degree view that you can get over here. uh, yeah, basically it's a 360-degree view. So this is how it looks like in Blender, and this is how it looks like in real life. And as I said, there were some parts which we weren't able to print properly due to some technical issues and very little time, you know, that we had. But we believe that once we get more time, more expertise, when we are mentored by the right people, and when we reach out to the right people and gain more mentorship, get mentored by them, and do more research, I believe we can do great stuff. Because in very less amount of time, I believe that we have come up with a solution that actually can create an impact. And this is a picture gallery that you guys can go through. This is how our design and our whole solution looks like, the hydrodynamic drag device. So yeah, I mean, that's it. It's thank you for your attention and support. We are dedicated, we are actually very dedicated to advancing coastal resilience and protecting the communities from natural disasters, because most of our teammates are, a lot of us are from coastal cities. I am not from a coastal, I do not live in a coastal city, but one of my teammate, he lives in Chennai, so he lives from in a coastal city. We have one of my teammates, Hao Yang, lives in Shanghai. Uh, so yeah, I'm basically, the thing is that we were able to create such a nice project because we all of us are from a different place. We all brought a very different perspective, a very nice point of view through which all of us could understand each other, come up with new ideas, and we could come up with such an amazing idea of ours. So yeah, we really appreciate the work that NYAS is doing and empowering students. And we are the team Extreme Resilience, and we are really really passionate about creating innovative solutions for a safer future. So yeah, thank you so much for listening to us. We really appreciate it. Thank you. Thank you guys.